This is easy, and it is. The question is just return the majority element, which is any element that appears more than the floor of n divided by 2 times. You may assume that majority element always exists in the array. Now, this is quite easy, right? If you just go through the regular approach, right? Perhaps you have like a table or a dictionary, and then you just iterate through this and you count the number of each unique elements right in there, and then anything that's above the length of the array divided by 2 floored is your majority element, and then you just return that. So we're not going to talk about that. We're actually going to talk about this much harder one, which is how do you solve in linear time in O1 space. And so I thought about this while I got stuck, and then I kind of looked at the discussions, and it kind of, because for me, the whole learning process is less of just solving these problems, and it's more of like, well, if I come across these questions or these like type questions in an interview, how would I go about solving it? Now, I guess for my particular interview, it doesn't matter too much because they told me it doesn't matter what complexity I solve it in because I can optimize in real job, so that's pretty cool. But just for this brief video, I think when they say O of n, linear time, or things on nature, then you kind of have to think about you're iterating through the array once or maybe twice, and in this case. Let's just start with the base case and maybe iterate through once. And maybe it's some kind of a DP situation, or you have some kind of pointer that evolves over time. And then in this case, what's special about an element that appears more than half the time? I got to thinking like, well, it has to be either in the, they both have to be on the edges of the array. If you don't have, so either they have to be on both edges of the array, or at least one of them has to be kind of stuck together, meaning like I and I plus 1 has to have the same element, things of that nature. So I'm kind of thinking like, well, how do I go about like thinking about this? And I think one thing that might help is if I were to do this, just start like this, and kind of just solving, because we have to iterate, like forward iterate, and I don't think there's any difference forward iterating and backward iterating this array, because like the problem's the same. So if we forward iterate and solve for this base case, then we could probably come up with something like this, and then probably solve for this, and probably solve for this, and then probably solve for that, right? And then once we kind of build out that solution, then we're good. Because I think the hardest part for me is like, I mean, there's a set of tricks you can memorize and a set of tools you can use in your toolbox, but for this problem, it's like, but how do I actually craft the solution from scratch if I have no idea? And let's just solve for the 2 case, right? If the element is 1, so if you say, well, if length num is 1, then you return, your num's 0. But I don't want to do that because I want to expand the solution to, these other cases. So I don't want to special cases. So perhaps we can just say, hey, my candidate is going to be num's 0, right? And then later we'll just return candidate, right? So now for the rest of the array, what can we say? One thing I know is that there's kind of like a lot of adjacency things with this, just like meaning the elements are going to be sort of next to each other if you have more than half of the array as those things, because like, because if you have more than half the array, then and let's say you don't have an element here, right? Your 2 is dropped here, then your 2 is here, or here, right? But then in any case, you're kind of guaranteed to have like these 2's kind of like being connected, and a gut feel is that like, you might have this sort of connection. So like this connects to a 2 more often than any other elements connect to each other to an extent. So we might, say something like, well, okay, so like candidate, something like this. And then maybe you have like some kind of like a count plus equals 1. And then so yeah. And then so what if like, so in this case, it doesn't really matter this count, because then there's no other candidates to switch, right? What about this case, right? If it's this case and then we have like count is 0, count is 1, and what do you want to do here? Or rather, what do you want to do here? I guess this case isn't a valid case because I think it says you may assume that the majority element always exists in the array, and if it's 2 of each, then by definition, neither a majority element. So, so in this case, right, we have 2, 2, and then we kind of need a way to say, well, 1, 1, 1. We need to revert back to 1 as perhaps a candidate. Right, so in this case, we have 1, and then perhaps we can make it go to 0. So maybe actually start 1. So if this is equal to this one, then actually there's kind of 2 of these consecutive ones, and then like if you have like 2, 2, 1, then your majority is still a 2. And then kind of like that kind of kills the weight of this 2. Like the more ones you populate, the less count you have. And then on this stage, you have count equals 0. And then I guess either 1 or 0 could be the candidate. And then here, I guess I don't really ever want to go to -1 with the count, because that's really assuming a lot about this 2. Because then if you go to -1 with the count, then how do you ever swing back? So it's almost like if I go to 0, maybe does that work? So here, then 1 is like the new thing. So if it's a 1 here, then we go ahead and say, well, okay, count is 1, and I'm the majority. But then if it's a 2 over here, so like these kind of like these 2 1s annihilate these 2s. But if it's a 2 over here, I don't want to go to -1, so it's almost like this. And then this will say, well, okay, if I have like a bunch of 1, 2, then I'll just keep swapping. And then basically it doesn't matter if I keep swapping. So like this is now the majority, this is now the majority. And basically what'll happen is when you're here, all the information that's to the left of it gets propagated indirectly, because if it's these are now like this, but then this is your kind of your remainder, so now that's your majority, right? But then this is the same case as this, right? And so like once you go here, you can say like, well, this is just 2 and 2 and 2. And then you can kind of flip-flop, and this annihilates this annihilates this, and then at the end, this last element is just the same case as this. Yeah, so, yeah, I mean, I guess here you could start at 0, actually. It's probably more symmetric if you do it, because in this case, I want this case and this case to be the same. So if I start at 0, this is 1, this is 0, but then this would make this the majority. Unless I do else if here. So then this is a 0. And then this is a 1. 0, 0, 0, 0, 0, 0. 1, 0. What happens if I do this? So one, then we go to 0. But then this is out of sync, so we can't do that. So again, if we have 0 here, and then we have 1 here, and then here, we would have 0, and then now my candidate is 1, even though this is a 2 majority. Maybe we can do something like this. Reset the count to 1. So 1, 2, 1. This is 0. But since we're assuming this is now a majority, we go to 1 again, and then we go to 0. And then so this is candidate, and then we set it to 1, and then 0, 1, 0, 1, 0, 1. So I can go to 0 again, make this new candidate, or we can say 2. And then now this case is going to be symmetric to this case where it's 2. And then I guess it doesn't really matter if it's 1. It's really like x, right? So like, for example, if it's like 1, 3, 1, it kind of doesn't matter. We kind of treat it the same. Like these two will annihilate this, and then this your new candidate. But then this will kind of cancel it out, make this your new candidate, and then this guy will kind of increment. So yeah. So it seems like, yeah, like this could work. Let's run the code and debug. let's try. Yeah, and then that's kind of how I might going forward, like just like these base case kind of stuff is good, but then like how do you come up with this like count of anything? Well, like I guess you have to count something, right? Because if you want the majority, then you probably need to know something about the frequency of when things happen. And I feel like the connectivity of the majority elements are just gonna be more connected to themselves than the minority elements, right? So you can kind of do this equals, and you can kind of think of it as like an edge between this node and this node, right? And then like the edges are basically where the two adjacent elements are the same. And then like the other case I noticed was like if you have a majority element where they're not connected at all, then it's like this. It must be like this. And must be an odd number, because if you're an even number, then you must have one of these be stuck, like you must have an additional 2, otherwise it's not a majority element. But if it's an odd number, then you can keep assuming that whatever new is your new candidate, because you can keep resetting, and you're guaranteed at the end that you'll get this reset here. So anyway, that's it for this one. More from my own education and kind of verbalizing how I would start from the very small problem and then expand out, and then just double checking my thinking with like the counts, like the counts here, the count looking at like starting from here should be exactly the same from here, and then the count after this interval should be the same as this interval, right? And that's kind of when you know you have sort of like a symmetric solution. Whereas before I have like that 1 or 0 issue, and like this was 0, whereas this is reset to 1, and that could have worked, but maybe, I don't know, it could have been pretty iffy as well. So anyway, that's it for this one. I'll see you in the next.